Every hazard control, interlock system, and ventilation upgrade you recommend requires corporate funding. In practice, a safety measure is a capital allocation request. Friction occurs because safety professionals natively speak the language of compliance, risk matrices, and incident rates. Executive leadership evaluates decisions through a different lens: financial justification, operational efficiency, and return on investment. A safety recommendation lacking economic justification is rarely implemented, regardless of its operational merit. To bridge these two perspectives, you must utilize engineering economics. This discipline involves the application of financial tools to evaluate upfront safety investments, model the monetary value of risk reduction, and calculate lifecycle costs across an asset's useful life. We will construct the mathematical framework required to determine the precise dollar value of safety controls. Mastering these financial translation tools allows you to present safety as a measurable and strategically justified corporate investment. Before evaluating complex systems, we must map the behavior of capital over time. The prerequisite for all financial modeling is percentage conversion. In every equation we use, the interest rate, represented by the variable I, must be inputted as the percentage divided by 100. This line graph shows simple interest. The formula calculates future value, F, by multiplying the principal investment, P, by 1 plus the interest rate times the number of periods, N. The rate of ascent remains constant because interest is calculated exclusively on the original principal. Because it ignores the accumulation of previous interest, this equation is limited to simplified or short-term evaluations. Real-world capital modeling strictly requires compound interest. This comparison shows the difference in growth. The graph on the right introduces the exponential growth expression central to compound interest, 1 plus I raised to the power of n. In this model, interest is calculated on both the original principal and all previously accumulated interest, driving the curve upward. Because the variable n sits in the exponent, time is the dominant factor. Even slight changes to the number of periods alter the final financial figure significantly. For the safety professional, these compound models dictate the reality of cost escalation and inflation over the lifespan of a facility. Failing to use compound models when projecting long-term liabilities ensures that the resulting estimate will fall short of the actual financial exposure as time passes. This exponential behavior leads to the principle that dictates corporate capital allocation, the time value of money. This concept states that money available today holds greater value than the exact same numerical amount in the future. Inflation is the primary driver of this erosion, as it reduces future purchasing power year over year. The secondary driver is opportunity cost. Capital that is not deployed today cannot be invested to generate a return. This cash flow diagram maps these shifts. We begin with our present value, P, placed at year 0. Applying the future value equation to this timeline demonstrates how purchasing power declines as the capital moves rightward into the future. We use this equation to estimate how much replacement equipment will cost in 5 years, or how the financial penalty of an incident will escalate. The time value of money provides the mechanism required to compare an immediate upfront safety investment against the inflated financial consequences of a future accident. We apply the time value of money through 4 specific factors used to construct and evaluate corporate budgets. This matrix maps the 4 factors. First is the series compound amount factor. It calculates how repeated, equal periodic payments accumulate into a single future sum. This is used to model long-term funding strategies and build safety reserve accounts. Second is the sinking fund factor. This determines exactly how much capital must be saved each period to hit a specific future target amount. It is utilized for planning the replacement of aging safety infrastructure without triggering sudden shocks to the corporate budget. Third is the capital recovery factor. This converts a lump sum initial investment into an equivalent series of annual costs. This allows for an accurate comparison of the true cost of different safety equipment models over their respective lifespans. Finally, we use the present worth factor. This identifies a series of future payments and discounts them back into today's monetary value. The present worth factor provides the logic needed to show that the cumulative value of avoided accident costs over several years justifies the expense of a safety control today. Securing the initial purchase is only the first phase. Safety equipment represents a long-term commitment. Lifecycle costing integrates all financial phases of an asset's existence, from installation through maintenance and operation to eventual disposal. Over a decade of use, the costs of maintenance and daily operation frequently exceed the initial price tag. When these long-term safety assets require corporate financing, we must account for amortization. In an amortized loan, the total payment amount remains constant each period, but the internal ratio shifts. The interest portion decreases because it is calculated only on the remaining balance of the loan. Factoring in this shifting interest burden is necessary for proper cost allocation over the asset's lifespan. Incorporating lifecycle costing and amortization prevents a common analytical error. Assuming a system with the lowest upfront cost will be the most economical solution over its useful life. Regardless of the industry, organizations rely on a specific financial threshold to authorize expenditures. A proposed safety solution is mathematically and strategically viable only when it satisfies this exact inequality. To apply this in a professional or exam context, follow a strict workflow. First, identify the required variable, then convert percentages to decimals. Next, select the correct formula, based on the cash flow structure, verifying that your units of time align with your interest rate. Finally, perform a logical validation. Review the result to ensure the figure makes sense given the initial inputs. Mastering engineering economics allows you to move beyond the role of a compliance enforcer. You become a strategic influencer, capable of proving that safety is a high-yield investment.